Okay. So now let us see this example. C over H, CH3, here OH hydrogen, and this one hydrogen H, here CH3 COH. Okay. Now these two are the mirror images each other. These two are the mirror images each other. Okay. Now here let us say this is dextrorotated D-lactic acid. Its name is lactic acid. Now it is L-lactic acid. L-lactic acid, D-lactic acid and L-lactic acid. Okay. So here in this case, it is a dextrorotator. Rotates PPL to the right side. Rotates PPL to the left side. Okay. For suppose here plus x degrees. Now it is a minus x degrees because exactly mirror images and non-superimposable. Okay. The compounds which are mirror images and non-superimposable. Okay. Now here this lactic acid and lactic acid are mirror images. The mirror images each other and non-superimposable. That pair of compounds are called as enantiomers. That pair of compounds are called as enantiomers or optical antipodes. Optical antipodes. Enantiomers. Okay. Enantiomers are optically antipodes. That means here different optical activity. The same compound, okay, same connectivity, but different spatial arrangement, mirror images each other. This are the mirror images each other. This compound rotates PPL to the right side, then its mirror image rotates PPL to the left side. If it rotates PPL to the left side, then its mirror image rotates PPL to the right side. Okay. That is, one is dextro, one is the levo. So the pair of mirror images which are non-superimposable and must be optically active. This one rotates PPL, this one also rotates PPL. Those pair of compounds are called as the enantiomers or optically antipodes. Enantiomers are optical antipodes. Okay, this definition is important. Enantiomers. Enantiomers means here the pair of compounds which are mirror images each other and optically active. Optically active. Those are called as enantiomers. Here enantiomers have the same physical and chemical properties. Enantiomers have the same physical and chemical properties. Okay. So generally what is the definition for the isomers? The compounds which have same molecular formula but different physical and chemical properties. That is the isomerism actually. But in this case, these compounds, these enantiomers have the same physical property, but there is only one different property in optical rotation. In polarimeter experiment, this one rotates PPL to the right side, this one rotates PPL to the left side. There is the only one property is different. That is the optical rotation. Optical rotation is different for these two compounds. That's why these are the optical isomers. The pair of compounds which are mirror images and non-superimposable are called as enantiomers. Okay, and these enantiomers have the different physical and chemical properties. Sorry, same physical and chemical properties. Okay, and enantiomers must be optically active. Okay, if the compounds are optically active, those can be said to be enantiomers. Okay, so enantiomers must not be optically inactive. If those compounds are not optically active, those are not called as the enantiomers. Okay, so write the definition. Side heading: enantiomers are optical antipodes. Enantiomers are optical antipodes. Enantiomers are optical antipodes. Okay, compounds which are mirror images. Compounds which are mirror images. Compounds which are mirror images and non-superimposable. And non-superimposable. And non-superimposable on each other. Okay, these two compounds are non-superimposable. You can see like this. Non-superimposable on each other. Non-superimposable on each other are called as enantiomers. 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 Enantiomers have same physical and chemical properties. 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 But differ in optical rotation. Differ in optical rotation. But differ in optical rotation. Differ in optical rotation. That means here direction is different. Magnitude is same, but direction is different. And one more point, enantiomers must be optically active. 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 Okay. Next one. First, suppose this is also compounds here pH, OH, here H. This is mandelic acid. This is mandelic acid. First, suppose it is a plus mandelic acid. Its mirror image OH, H. Here pH, COH. This is minus mandelic acid. That means it is a dextro, it is a levo. Generally, we cannot say which is a dextro, which is a levo. Just let us say if it is a D, it is a L. If it is a L, it is a dextro. Okay. So again, these two are the enantiomers, the pair of compounds which are mirror images and non-superimposable. Okay. Or suppose we can write like this here, COOH, here CH3. This one above the plane OH, this one below the plane H. Okay, this one COOH, here CH3, this one OH, this one above the plane hydrogen. Now here these two are the mirror images because OH above the plane, here OH below the plane. It is a mirror image of this compound. This hydrogen below the plane, this hydrogen above the plane. So these two are the mirror images. These two are the mirror images. So here enantiomers. These two are the enantiomers. Okay, that's it. And next, actually here, if molecule contains plane of symmetry, center of symmetry, or alternative axis symmetry, that compound is optically inactive compound. Okay, how that molecule is optically inactive molecule? Okay, I'm repeating again. If molecule contains plane of symmetry or center of symmetry or alternative axis symmetry, then the compound is optically inactive compound. Its optical rotation is 0. Okay, how that has a 0 optical rotation? For suppose COOH, here I am writing COOH, here OH, here OH, here hydrogen, this hydrogen. Actually here it is a chiral carbon, it is a chiral carbon. Already we said this one, it is a tartaric acid. Tartaric acid. Okay. Now here this tartaric acid has 2 chiral carbons. Even though it has 2 chiral carbons, this compound is optically inactive compound. Okay. Even though it has 2 chiral carbons, this compound is optically inactive compound. Okay. Here this compound has 1 chiral carbon optically active. This one also optically active. But even though it has 2 chiral carbons, this compound is optically inactive compound. Okay. So actually here this one has no plane of symmetry because here this one cannot be cut into 2 equal halves. All are the different groups. Now in this case, this can be cut into 2 equal halves. Those 2 equal halves are the mirror images. Okay, HOH, COH, HOH, COH. Those 2 equal halves are the mirror images each. Now, when there is a possible of the plane of symmetry, here this half rotates PPL to the right side. For suppose plus 30 degrees. Here this half rotates PPL to the left side with minus 30 degrees. Because equal halves, these two are the equal half. One equal half rotates PPL to the right side, other equal half rotates PPL to the left side. That means here its optical rotation is cancelled each other. It is known as the internal compensation. It is known as internal compensation. Okay, it is known as internal compensation. And those compounds are called as a meso compounds. This is meso-tartaric acid. It is a meso-tartaric acid. Okay. Here in this case, this one can be cut into two equal halves, and one equal of optical rotation is plus 30, other equal of optical rotation minus 30. So total optical rotation in polarimeter experiment is 0. Then the compound is optically inactive compound. And these compounds are called as the meso compounds. Meso means here middle. Meso means middle. There is a possibility of the plane of symmetry in middle of the molecule. Okay, this compound is optically inactive. All meso compounds are optically inactive compounds because of this symmetry. Okay, because of symmetry. So that's why here, what are the conditions for optical activity? Your chiral carbon is not a 100% compulsory condition. That molecule must not possess plane of symmetry, center of symmetry, or alternating axis of symmetry. Now, even though it has a chiral carbons, because of the plane of symmetry, here internal compensation took place. Then this compound is optically inactive compound. Those type of compounds are called as the meso compounds. Okay, that's it. Side heading meso compounds. Meso compounds. Meso compounds. Meso compounds. Okay, write down. The compound, even though compound has chiral carbons, even though compound has chiral carbons, even though compound has chiral carbon, even though compound has chiral carbons, due to plane of symmetry or due to center of symmetry, due to plane of symmetry or center of symmetry, it is optically inactive. It is optically inactive. It is optically inactive. It is optically inactive. Such type of compounds are called as meso compounds. Such type of compounds are called as meso compounds. Such type of compounds are called as meso compounds. Okay, in next line, in the given compound, in the below compound, in the below compound, the below compound, in the below compound, optical rotation of the optical rotation of half of the molecule, optical rotation of half of the molecule, optical rotation of half of the molecule is cancelled by other equal of is cancelled by other equal of is cancelled by other equal of because it has a plane of symmetry, 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 and it is known as internal compensation, and it is known as internal compensation, internal compensation, internal compensation, and then finally its optical rotation is 0, its optical rotation is 0, comma optically inactive molecule, and comma optically inactive molecule, and optically inactive molecules. All meso compounds are optically inactive. All meso compounds are optically inactive. All meso compounds are optically inactive. Okay, write down this one. The meso tartaric acid. The meso tartaric acid. Meso tartaric acid. Okay. Okay. For suppose you can see here COOH, here COOH, here OH, here hydrogen. This is OH hydrogen. Its mirror image HOH, here OH hydrogen. This one COOH and this one COOH. Okay. Now these two are the mirror images. These two are the mirror images. This one has no plane of symmetry. Okay. This one has no plane of symmetry. This molecule equal-offs are not mirror images. Okay. This molecule equal-offs are the mirror images. This molecule equal-offs are not mirror images. This molecule equal-offs are not mirror images. Okay. So here these two are the mirror images each other. So this compound is optically active. This compound is optically active. The pair of compounds which are mirror images each other and optically active. For suppose this is D-tartaric acid. This is D-tartaric acid. This is L-tartaric acid. And these two are the enantiomers. These two are the enantiomers. Okay. That means here with two chiral carbons, that compound may be optically active or inactive. For suppose I am writing like this here COOH, here CH3, here OH, here OH, hydrogen, this hydrogen. So OH, hydrogen, this one OH, hydrogen, COOH and CH3. Now these two are the mirror images. This one has no plane of symmetry. This molecule cannot be cut into two equal halves. Okay, this one has no plane of symmetry. So here these compounds are optically active and mirror images. This pair of compounds are called as the enantiomers. This pair of compounds are called as enantiomers. For suppose you can see this one CH3 and CH3. This is the chlorine and this is the chlorine. Hydrogen, this hydrogen. Okay, now here this compound is optically inactive. For suppose let us take the mirror image of this compound, a Cl hydrogen, and here the CH3 and CH3. Now this one has a plane of symmetry. Of course these two are the mirror images. These two are the mirror images. But here there is a plane of symmetry. This is the equal. These two are the equal and mirror images each other. These two are the equal and mirror images each other. Okay. These two are the equals and mirror images each other. Now these two are the mirror images, but individually each compound is optically inactive. Okay. Individually each compound is optically inactive. The main point is here. Okay. Here in this case these two are the mirror images and non-superimposable. These two are the mirror images and non-superimposable. So these compounds are the enantiomers and these two are the enantiomers because there is no symmetry. Here there is a symmetry, equal halves and mirror images. So optical rotation is cancelled. Internal compensation called as a meso compound. Now here again this one has a plane of symmetry, equal halves, optical rotation is cancelled each other. Okay, here also optical rotation is cancelled each other. Even though here mirror images, individually this compound is optically inactive compound. So these are not the enantiomers. This is the meso compound, meso 2,3 dichlorobutane. This is also meso 2,3 dichlorobutane. These are not the enantiomers. The main point is these are the enantiomers. Even though these are the mirror images, but not enantiomers. Here these are the enantiomers, mirror images, and each one is optically active. Here optically active, here optically active, and mirror images, enantiomers. Here this compound is optically inactive compound. So here, even though these two are the mirror images, these are not the enantiomers. Here, what I am saying here, these are not the mirror image, these are not the enantiomers. Okay, because this compound is optically inactive. Enantiomers must be optically active. Enantiomers means here the pair of compounds, okay, which are mirror images each other and non-superimposable and must be optically active. This compound is optically inactive. This compound is optically inactive. Of course, these are the mirror images, let us say. Okay, so, but here optically inactive compound. So here this type of compounds, the compound with chiral carbon and optically inactive. Okay, the optically inactive compound with chiral carbon is a meso compound. Optically inactive compound, optical inactivity ఎలా వచ్చింది? How it gains optical inactivity? Because of the plane of symmetry. So because of plane of symmetry, half of the rotation, for suppose plus x degrees, remaining half rotation minus x degrees. So cancel each other. Okay. So here meso 2,3 dichlorobutane. Now here it is a meso compound. This one also meso compound. This one also meso compound. Here two meso compounds are identical. Two meso compounds are identical, are also called as homomers. Okay, important point. Here let us make a note of it. Two meso compounds. Okay, two meso compounds are homomers. Two meso compounds are homomers are identical. Two meso compounds or homomers are identical. It is a meso compound because plane of symmetry cancel each other. Okay, internal compensation is there. Here internal compensation is there. So it is a meso compound. These two are the homomers, equal. It is a single compound, not two. Okay, here in this case we can separate these two. Okay, because one is a dextrorotatory, one is a levorotatory. Initially we said that stereoisomers, that means here configurational isomers are not interconvertible and isolable and resolvable. Okay, configurational isomers are non-interconvertible. We can resolve, we can separate. Okay, here in this case we can separate these two individually. One is the dextro, one is the levo. But here in this case we cannot separate. Okay, these two are the identical. That means here one compound. Okay, either one is a meso compound. Two meso compounds are the homomers or identical. That is the important point. Okay, so here what are the important points in this case? The pair of compounds which are mirror images, non-superimposable and must be optical active. Those are the enantiomers. Okay. If compound has a plane of symmetry or center of symmetry, even though it has a chiral carbon, its optical activity is zero. Those are called as the meso compounds. That is the internal compensation. Meso compounds are always optically inactive due to internal compensation. Okay, that's it. So right answer. Okay. So two meso compounds are the identical or homomers. Enantiomers must be optically active. Meso compounds are optically inactive due to internal compensation or due to plane of symmetry or center of symmetry. Okay. So next, write one more point. Compound with one chiral carbon. Compound with one chiral carbon. Compound with one chiral carbon is always optically active. Is always optically active. Compound with one chiral carbon is always optically active. Okay. So now compounds with two chiral carbon or more than one chiral carbon, its optical activity depends on symmetry, plane of symmetry, center of symmetry. Okay, like that. Okay, if you want that, you can write. With more than one chiral carbon, with more than one chiral carbon, its optical activity depends on, its optical activity depends on symmetry, depends on symmetry, depends on symmetry.